So, then let's start our exercise B. So we have now B from our first task in our today's exercise. And as I mentioned, we want to define our forcing function, our normalized forcing function. And we will define that as the following. And the forcing function consists of the sum of k basis functions, and the basis functions I simply call theta, and the setters are of course also dependent of the parameter z, and now gets weighted with the weight omega I, and again multiplied with z, with the parameter z. And in order to normalize the generated values of these forcing functions, I simply divide through the sum of all forcing functions evaluated at time that. Okay. And this is simply our definition for our forcing functions. For our forcing function. And now we have to, here's missing a J. And now we have to define what are exactly our basis function here. And these basis function we are using in our lecture here are normalized radial basis functions. So normalized radial basis functions. So and they are defined as, I'm sorry, this was not on purpose. We make it back. So, and they are defined as the following, as theta from I, and dependent of the parameters that is the exponential of minus 0.5 multiplied by z minus ci squared and divided by hi. And these are our definition, these are the definition of a normalized radial basis function. So if you are more interested if you are interested in which other basis functions exist, just have a look. Just for example, just Google basis functions, and you will find a wide area of possible basis function which you could use here for this forcing function, or to generate this forcing function. But here in our lecture we will simply use these normalized radial basis functions. Okay. So, and what we are now doing is to have a look into the structure of these basis functions. So we have here two parameters, that Ci and Hi, and these parameters define how the radial basis function looks like. And in order to have a weight range on different basis functions, we have to choose k. We have to choose k radial basis functions, and each of them should have different parameters Ci and Hi, so that we get a wide range of possible radial basis functions, so that we can combine that with convenient weights in order to generate a real good forcing function to follow a desired trajectory. Okay, let's have a look how the basis functions really looks like. So again, I will simply write down the equation. So we have here again our definition of our radial basis functions. And now I want to give you an idea about how these parameters Ci and Hi defines the given radial basis function. So let's have a look on our graph. We have here the 1, and we have here also a 1. This is that, and this is theta I of that. Okay. So let's have a look. First, let's say Hi is constant. For example, Hi is simply 0.1, and we vary simply the Ci. So and what we get then is simply the following. For the first, we would get something like that. The second function would be something like that, maybe, if we are saying, okay, we define here simply our different values, 0.2, 0.4, 0.6, 0.8. And what I'm doing is I will define 6 functions. Ci is 0, 0.2 up to 1. Okay. So this function would be with Ci is equal to 0. And the next function I will draw is kind of this function. And this function will look like something like this. Okay. And this is, maybe you can guess it right now, it's simply Ci is 0.2. And I can draw another function, would be maybe look like this. And we got here, we got here now you should be able to guess it. Now it's simply Ci is equal to 0.4. Okay. So the Ci, or the C, simply defines the peak, or where the peak lies of the radial basis function. So if the peak lies, if the C is 0.4, the peak where the radial basis function hits 1 is at Z 0.4. Okay. So just to make this clear, if this is 0.4, then we hit the 1 at that is equal to 0.4. Okay, this is what the C does on the radial basis functions. But what does the H? And the H defines the width of the radial basis function. Okay, these radial basis functions are simply with H is equal to 0.1. So, and when we look now, for example, let me point this out with green. When we now define another H, for example 0.01, then the radius basis function, the width, gets much smaller. So, for example, we could draw this here. Okay, and this radial basis function has now, for example, c is 0.2 and h is 0.01. So again, just for repetition, the z, so that's the c. C defines the peak, and the h defines the width of the radial basis function. Okay, so now we have an idea how such radial basis function looks like. And again, if you want to do a forcing functions out from these radial basis functions, you really should choose a wide range of different radial basis functions. So vary these both parameters. And if you have done that, then you can start to learn the weights. And we will discuss how to learn the weights now in part C of the first task. Okay. So let's start with the last part of the first task. It's part C. And again, I will simply write down the equation for the forcing function, which is again dependent from the weights W. So again, the equation of the forcing function was the following. It's a sum of the normalized basis functions, or radial basis function in our case. And these basing functions are of course dependent on that. And here are the weights, Wi, and we are multiplying this by that again, and normalizing this by simply dividing through the sum of our basis functions. Okay, this is simply the definition of our forcing function. And we can now, or what we want now, is to learn these parameters. And we have to learn these parameters by given examples. So, and in order to do so, we are simply rewriting this equation into matrix form. And in matrix form, this equation will look like the following. Here again we have, okay, we'll write this a little bit clearer. Here again we have our forcing function, but now we are rewriting this as a vector, and this vector is transposed and multiplied by a weighting vector W. And this weighting vector W is what we want to estimate by using measurements or measurement data. And our psi is defined as the following. Psi I of that is simply theta I multiplied by that, dependent of that and multiplied by that. And again, through the sum, also the normalization term of all basis functions. Okay, so this is a vector, and this is a vector, and this is a vector. Okay. And imagine now we are knowing how our forcing function should look like. How can we know that? We can know that by simply having done some measurements and using our parameterized trajectory generator model. Okay, so for example, we have now measured a lot, or we have now received a lot of data from measurements. And again, I will simply write that down. So that we have it again here. This was psi transposed of that multiplied by w. These are both vectors. And now we need to have data here. This should be our measurement data. And we can get this by making measurements about the position x, the velocity, and the acceleration of our desired trajectory. So I just call that t for trajectory. And these are our measurements. And from these measurements, we can now calculate our forcing function, or our required forcing function by simply rewriting our parameterized trajectory generator to the following. We got then simply x dot dot is equal to so the forcing function is equal to x dot dot minus tau alpha tau squared alpha beta g minus x dot through tau. Okay, and now we can simply add here a t to indicate that these are now our measurements, and then we have here also a t to indicate these are now really our measurements. So we got values for our forcing functions from our measurements, and our measurements of course should be all dependent of that. We should normalize our measurements as well. Okay, so what we have now is simply we have here a lot of data. So this will be a vector, and we have again also here a vector, and we will get here a vector for every z. So if we get here a vector for every z, we get for a lot of z's a matrix. So again, this is a matrix, vector, and matrix, vector. This is a vector. Okay. So, and these vectors, so again, we got like, we should make it consequently. So this is our measurements, ft, dependent on the weights w of that is equal to psi transposed of z multiplied by w. And this is a vector. And we can now define that as a matrix. And this vector here, this vector will have will be a vector like n1 with the size n1, and n is the number of measurement points. Number of measurements. Okay, and what we can do now is to use simple regression, and we will use here the least square method, so that the squared error will be minimized of the problem in order to find our optimized weighting parameters w. And to do so, I will start now to define it a little bit different.